I am told that the least desirable speaking slot in a conference is the first talk in the morning, the night after the banquet. So I owe an apology to the speaker for having scheduled him there, but I think he can make it, he can handle it. It's my pleasure to introduce Mark Behrens, who perhaps I have known longer than maybe anyone else in the room right now, although there are a couple of other people here who are quite close. Anyway, he will speak about C2 motivic, C2 equivariant homotopy groups from real.
Sorry, I tacked my title and put it into symbols. What I want to do is I want to talk about let's say you have a real motivic spectrum X. Okay, so I'm going to write this for the category of real motivic spectra, and the problem I want to discuss is how do we say you know something about the real motivic homotopy groups of X, then how do you describe the C2 equivariant homotopy groups of the Betti realization of X? Okay, so that's the topic of the talk. So let me introduce some notation. So as I already indicated, I want this to be the category of real motivic spectra, but let me be a little pickier here. This is actually the category of cellular. So I'm only interested in cellular real motivic spectra. That is things, so I'll say a moment when I get some more notation on the board. For people that don't know what that means, I'll say what that means. Cellular real motivic, two complete real motivic spectra. And then I will use SPC2 to denote the category of cellular, let me just say two complete genuine C2 equivariant spectra. Now, since it's well known that there is a functor called Betti realization that goes from the category of real motivic spectra to C2 equivariant spectra. And roughly speaking, what you do is you take your real motivic spectrum and you take its C points. And then, well, because the thing's defined over R, this thing gets a C2 action. And because this is a P1 spectrum, now this thing is like a spectrum with respect to the sphere, the one-point compactification of the regular representation, so it's a genuine equivariant spectrum. Okay, so and so then what we get is we have the two objects we're interested in. So before I introduce those objects, let me just say that both of these categories have a notion of a sphere, and I'm going to stick to the motivic grading that we've seen in some previous talks, the Sij, which will denote this kind of motivic sphere if we're in the motivic context, and it will denote this kind of equivariant sphere if we're in the C2 equivariant context, where sigma is the sign representation. And then I will, instead of indexing things pi star star, I'll use the equivariant convention of using the fancy star because it's less stars to write down. Okay, so we have the homotopy groups. Say again, X is a real motivic spectrum. Already my notation is getting messed up here. There we go. So this guy is, of course, the maps in the real motivic stable homotopy category from S star into X. The first thing to note about these two kinds of homotopy groups is that because realization is a homotopy functor, it gives you a homomorphism between these groups. Oh, so the thing I wanted to say over here was that the realization of the Sij in the real motivic sense is the Sij in the C2 equivariant sense. So our indexing matches up. So because you got a functor, you get a map. And so there's a homomorphism between these two groups. This homomorphism was studied by Dugger and Isaksen. Who showed that if you write star as S comma W, then this thing is an iso for some conditions. And the conditions are S greater than or equal to 3W minus 5 or S less than or equal to minus 1. Okay? So that already shows there's a close relationship between these homotopy groups. They're simply the same in some huge range.
Mark?
Yeah.
I think that's true like for S00 or something, right? But you'd have to
Oh, sorry. I am sorry. That totally depends on, say, X equals S00. Thank you, Dan. It would be wildly false if I even let X be a different sphere. Yes. So I mean, there's a close relationship between the real motivic homotopy groups of spheres and the C2 equivariant homotopy groups of spheres. They're the same in a range. Okay? So, but even in the case of the sphere, there's a region away from this where they're not the same. And I want to try to understand the differences between the two things. And then also we want X to be allowed to be not S00, though what I'm going to say doesn't supersede this. In fact, this interplays closely with what I'm going to say. I think there's something very interesting to say here. Right. So the goal. So the question is so the claim, which is the main point of this talk, is if you know like really well, I'll have to explain what I mean by this. If you really understand the real motivic homotopy groups of X, you can get read off the C2 equivariant homotopy groups of the realization. Okay, and let me stress, I can't stress this enough. I mean, the two complete is something that's important in what I'm saying. This cellular thing is super important. So let me say a word about what I mean by that. So the cellular is built as a CW object. Not really CW, but cellular object. Okay, let me just say built out of SIJs. Okay, that's what cellular means. Okay, So in the real motivic, in the motivic context, not everything is cellular, but I'm only interested in those guys. So I'm only making a claim for cellular guys. For non-cellular guys, I know nothing. Sorry, question? Is there? Yeah.
It's not at all clear to me whether you're working with two completions of cellular things or things which are too complete and cellular, and I don't know if those things are the same.
That's a good question, and maybe I wish I had my collaborator here to answer it. I think that so we're take the cellular category and then make the equivalences the two complete equivalences. So does that answer it? Okay, cool. Any other? Okay. Okay, so that's super important. So I'm not going to say cellular again, but of course I always mean it. Otherwise, I don't know anything. Okay, right. So a good point of reference is, so let's back up. The backstory here is the complex motivic case. So in the complex motivic case, you have so now SPC will be the category of this will be the category of cellular two complete. C motivic spectra, and then we have a Betti realization functor that goes from complex motivic spectra to ordinary spectra. And this is just given by, again, taking the C points, but if you're defined over C, you don't have any additional structure. You're just a spectrum. Okay, so then that gives rise to another version of this. So then we have a map from the homotopy, the complex motivic homotopy groups of X in a similar fashion. We have a homomorphism from here to, it's actually kind of important to know what does this thing do to Sij. So if you have Sij in the motivic context, this thing is just Si. It just forgets the J because the realization of GM is a circle, and so I get a map like so. Probably poorly written. Let's do it this way. There. I get a homomorphism like that. Now the thing is that there's this. So in the two, you have to be two complete for this to work out. In the two complete case, there's this element. So there's this element tau. So let me see here. So let's let HC denote the mod 2 Eilenberg-MacLane spectrum. So HC of a point is the coefficients of HC is famously F2 adjoin tau, where tau is a class in bad notation. I wanted to use absolute value for the degree, but I'm already using absolute value for there. Degree of tau equals 0 minus 1. And the thing is that this tau is in the Hurewicz image. So if you consider the complex motivic homotopy of the sphere, then this guy tau is actually in here. So there's a guy tau in here that maps over there. Okay. So in other words, these groups here you can localize with respect to tau. Now the other thing to know is that the realization of tau is 1. in pi 0 of the sphere. Okay? So tau, multiplication by tau over here doesn't do anything over here under this homomorphism. And therefore, this map factors through the tau localization. Okay? And the theorem I think this is due to Dugger and Isaksen. This is at least where I learned it from. Is that this map is an iso. Oh, I have to explain something what I mean here. So I'm going to localize at tau, and I'll set tau equal to 1. Okay? Then this thing is an iso for X cellular. So in the complex motivic case, this story has a really simple answer. You take tau and you invert it, and now you've got classical homotopy. The claim is going to be that something similar is happening over here, okay? That you take tau and invert it in a certain sense to get from the real motivic to the C2 equivariant, but it's a little more complicated. So let me
Mark, can I ask a question or make an
Sure.
observation that, strictly speaking, that isn't an isomorphism because the thing on the left is bigraded and the thing on the right is graded. So it's a,
Yeah,
it's an isomorphism with that caveat.
that's right. That's right. Yeah, it's very sloppily written. But you know what I mean.
Yeah, I do.
Yeah.
You said tau equals 1, that collapses the grade.
That's
Yeah.
right. An easy way to say that is to tensor the right side with the Laurent.
I could also have done that. I could have made a dummy tau over here and then done that. Anyway, it sounds like you guys all know what I mean, so I'm not worried. All right. This one actually. Okay, right. So now what we need to do is, so what are the characters? So how do things change in the real motivic case? In the real motivic case, let's let HR denote the mod 2 motivic, our motivic Allen-Berbick-Lane spectrum. And let's and the thing to know about this guy is it's a polynomial algebra on two guys called rho and tau. And here the degree of rho is -1, -1, and the degree of tau is that same 0, -1. And now I can't, now there's a little, so rho is an element. Rho is an element of pi -1, -1 of the sphere. So rho is in the Hurewicz image. But tau is not. That's a complication right away. Instead, you have to kill rho before you see tau. That is to say, let's let C rho denote the cofiber of rho. Then you consider then in pi 0 -1 r, you get this guy tau. Now, it's very easy for me to compute the homology of cofiber rho. Even if you don't know anything about motivic homotopy, you should be able to compute the homology of cofiber rho because it's a cofiber sequence. So what's going to happen, you're going to mod out by rho, and you'll just get a polynomial algebra on tau. So there's a Hurewicz map to cofiber rho here. Of course, this is just going to be a polynomial algebra on tau, and the tau here maps to the tau here. Okay, so that's one thing that's different. I want to invert tau, or I think I might have to invert tau, but I don't, it's not there. You have to kill rho before you can even get tau. Now another problem, okay, so before I go on to another problem, let me tell you some more notation. Let's let HC2 denote the mod 2. Well, this is the Eilenberg-MacLane spectrum. So this is an equivariant guy. It's the Eilenberg-MacLane spectrum for associated to the constant Mackey functor F2. And so here, the coefficients of this guy is, again, a polynomial algebra on two guys. Now they have different names, A and U. Okay? And then, but it's not just this. We saw in Dan's talk, Dan actually called them rho and tau because, I don't know, I guess are you born motivically and then switched equivariant? I don't know.
I changed names.
Okay, yeah, anyway, so you know, I was calling these rho and tau before I started talking with Doug about this, and he wouldn't let me do it, so then I changed it to A and U. So anyway, so there's this other chunk. Mod A infinity, U infinity. And this divisible chunk where the point of the divisible thing is called theta. So the picture people draw, my picture is going to look kind of like what happened in Dan's talk, but it's going to be upside down. So if I look at HIJ C2, the reason it looks upside down is because I'm doing homological and he was doing cohomological. So here's I and here's J, and here is tau, or sorry, U, and this is A. So here is the degree of U, or A, is -1, -1. The degree of U equals 0, -1. And then the degree of theta is this guy over here. So there's this divisible thing, this infinitely AU divisible thing. And the degree of theta is 0, 2. Okay, so this guy is usually called the negative cone. And it's like, yeah?
When you write this thing mod A, don't you mean, you're just saying it's just in the inverse powers of A and U? Is that what this A infinity, U infinity? What is that?
This is the co-limit of F2 adjoin A and U mod A to the I, U to the J, like that. That good?
Yeah.
Cool. All right. Right. So it's like the real motivic picture is just this. Okay. So I mean, already we're dealing homologically. The negative cone looks like a positive cone, but this is the positive side. This is the negative side. Okay. In the real motivic case, it's just this, where this is rho and this is tau. In the C2 equivariant case, you have this extra chunk, this negative cone, and the first thing you see, you sort of like are scared of the negative cone, okay? And maybe if anything, I want this talk is supposed to say that the negative cone is not scary. In fact, it's somehow that this is actually, the point of the talk is the C2 equivariant is simpler than the real motivic, even though it looks more complicated, okay? Now you're laughing, Stefan. Maybe foundationally, motivic is much more complicated than equivariant, but computationally, the
I was just laughing because some experts commented non-verbally on what you said.
Okay. So let's see here. Okay, so there's an analogy here. Oh, I wanted to say one more thing over here. So the same stuff happens, okay, over here. Namely, A, I can really describe these things concretely. That's one thing I can do equivariantly. Equivariantly, I can be super concrete, okay? So this guy A, it's given, so A is actually in pi minus 1 of the sphere. It's given by just including S0 into S, so it's A is sometimes called A sigma. It's the Euler class associated to the sign representation. You take the one-point compactification of the sign representation and you include S0, and that's A. Whereas U actually showed up in Agnes's talk. It's one of these orientation classes. It's not. U is not in the sphere, but U is an orientation for the sign representation. So that's one of these orientation maps from S0 to HC2 smash S sigma minus 1. However, the claim is that just like in this case, U lifts, U can also be regarded as being an element of pi 0 minus 1. You have to kill A before you get U. So you take the cofiber of A. And that might sound mysterious, but in the equivariant context, that's not mysterious at all. Because the thing to know when doing C2 equivariant homotopy is there's this cofiber sequence. C2 plus goes to S0, goes to S sigma. And so what that ends up telling you is that so what this ends up, what does this end up? All right, this is A, right? So then what this ends up telling you is that the cofiber of A is equivalent to the suspension spectrum of C2 plus. And so as such, there is this. Okay, I tried to pull that over on you guys. There is a shift, but then the shift ends up going away because of something I'm about to say. Okay.
Oh, you have to shift, right?
Huh? And this is true. Okay, I'm going to say this is okay. Maybe this is a theorem. Okay, but this is true.
Shift. You're missing an ordinary shift.
See, A is really a map from S minus sigma to S0.
That's right. That's right. Sorry, I'm thinking about A as a map from
Suspension of A, okay.
yes, up to a suspension. Okay, I mean, but I'm really thinking about A as being in pi minus 1. Okay. Okay.
I still don't understand why this is suspension.
Because A is really the desuspension of A.
So this is suspension 1 of A. A is a map from S minus 1 to S0.
But still, the code on that is.
No.
There is an additional confusion there. So let me clarify that. Okay. So here's the thing, right? Is that homotopy classes of maps from like X into Y smash C2 plus. C2 equivariant, this is self-dual. You could bring it over here, and then this is the same thing as non-equivariant maps. So I'm going to write XE for like the fixed points with respect to the trivial group. It's the corresponding the underlying non-equivariant spectra. Equivariant maps between these two guys are the same thing as non-equivariant maps. Okay, so when you're mapping into a suspension of C2 plus, actually the second variable, this motivic weight, if you like, or the number of sign representations, is actually irrelevant because you just care about the underlying non-equivariant thing. So it turns out that S1 minus sigma of cofiber of A is actually the same thing as cofiber of A. Yeah?
I think you can see it even more easily if you notice that A is self-dual, so then you just take the dual of the of that sequence you wrote.
Ooh, nice.
You just wrote the wrong sequence. I mean, A is not the map you labelled it as, that's all. It's okay.
Okay, but I have now with that, is it right?
I'm happy now.
Okay, great. Okay. Either way. Okay. Are people kind of happy?
Shouldn't the suspension only 1 and 1, 0? Either 1, 0 or 0, 1, and not 1, 1?
No, you suspend 1, 1 this thing. I stand by my sigma 1, 1. Anyway, this is, okay, you can ignore this if you like, but this is correct, okay? And the point is, and this actually gets back to another thing, because of this equivalence here, because smashing with C2 plus makes you non-equivariant, that means that cofiber, that sigma is actually orientable in the sense of Agnes's talk for cofiber of A theory. So that tells you that this U is an orientation for cofiber A. Now let's get on to another board, so I can't get past this quick enough. Okay, let's see, where's my eraser? Oh, and the thing I wanted to say over here was that the realization of rho is A, and the realization of tau. So if the realization of rho is A, then the realization of cofiber rho is cofiber A, and then the realization of tau is U. Okay. So this A and U are related, are the realization of rho and tau. Okay, now I want to give you an analogy that's going to explain the whole story. So this was sort of my motivation for this. So when I look at this picture, I see duality, okay? And it looks like a picture. It looks like the kinds of pictures actually that I've been seeing, since I was a graduate student. And I learned this sort of story from Doug Ravenel's 1984 paper. So in this paper, Doug studies various localizations of the BP spectrum, or like BP brackets N spectra, and you get this kind of phenomenon where you get like a copy of the spectrum and then this kind of backwards copy, and showing up when you do these localizations. So the analogy that I want to give is so here we have the real motivic, we have the realization functor to the C2 equivariant, and we have these guys rho and tau. And I want to compare this to the case where you take the category of P local spectra. I'm going to choose P to be greater than or equal to 3. And then I consider the localization map to E1 local spectra. So I think of these as being analogous and these as being analogous, and this localization functor as being analogous. And this is simpler than this because it's a localization. And under this analogy, this P, or this rho, is analogous to P. I hope they don't look too similar. And the tau is analogous to V1. Okay? And then the idea is that you don't have V1, but you have V1 in the cofiber of P. So when you take the mod P Moore spectrum, then in pi 2P minus 1 of the mod P Moore spectrum, you have this guy V1 in here. Now, I wanted to mention one other thing about U. I forgot to say this. This is a critical thing, actually. The critical thing to say is that in the equivariant world, so in both worlds, I can promote U to be a self-map. So I can regard U as being a self-map from 0, -1 cofiber of A to cofiber of A. However, and I can similarly view tau as being a self-map. These are ring spectra. So there's nothing to promote it to be a self-map cofiber of rho. Okay, the point here is that this guy is a map, but it's not an equivalence. But this guy is an equivalence. And this is sort of the underlying reason, this is the thing that's this is basically what it means to be an orientation, okay? That when you smash cofiber of A with S sigma -1, it just looks like cofiber of A smash S0.
Mark, in your analogy, is the left column also localization?
Do
Do we know if the left column is also localization?
I'm not going to speak to that. Maybe it is. I don't know. Maybe you guys will tell me immediately why it is, but I don't know that. But anyway, maybe it is. I don't know. Better get going here. Okay, so now, right, and so the point is that V1 is invertible, is an equivalence when you do the E1 localization. When you promote it to a self-map, once you take the E1 localization, it's an equivalence. Okay. Great. So let me go on and do an example. There's something else you have. You have chromatic fracture. So say I want to start with the homotopy groups of a p-local spectrum, and I want to get the homotopy groups of its E1 localization. Then I can use the chromatic fracture square to do so. Namely, the E1 localization is obtained. You start with the rationalization and the K1 localization, and then you patch them together over the rationalization of the K1 localization. And this is a homotopy pullback. Now this thing is easy to understand. This thing is simply what you get. This is simply what you get when you take X. Because we're working P locally, it's what you take X and you invert P. This thing is a little more complicated to say what it is, but it has a formula. And the formula is, so there's a little thing I need. I need that for J very much larger than I, if you take the mod P to the I more spectrum, it has a V1 to the J self-map. Okay? And then because of that, I can make sense of the V1 localization of the mod P to the I more spectrum. So this guy is, I can write this as the homotopy inverse limit. A formula for this, you take X, smash the mod P to the I more spectrum, and then you invert V1. And then take the homotopy inverse limit over I of these things. That's a formula for the K1 localization. And then this thing is kind of what it has to be. It's the inverse limit of X smash MP to the I, where you invert V1, and then at the very end you also invert P.
Completely illegible what you're writing.
Oh, that's terrible. Let's try to fix that. Is this other things illegible?
A little better.
Okay.
Bottom left.
The bottom thing, yeah.
You're right. Thank you.
Maybe this is important enough that I write it on a different board. How about that? Maybe I should avoid this red. Okay, let me write it over here. So the rationalization is that the K1 localization is this. Bless you. And the this guy, well, I already know what it is because I told you formulas for the other two, but I'll write it down anyway. It's this. Okay. Legible? Yep. Cool. Awesome. These are important formulas. Okay. Man. Okay, let me do an example and then get to the point of this talk. This is a really important example, so I better just do this. This is what happens in Ravenel's 84 paper, periodic localizations. So here's something that happens. So I'm going to do it through this lens. Ravenel does it through the monochromatic lens. I'm going to do it through this lens. So I'm going to draw the homotopy group. So I'm going to do x equals BP brackets 1. Okay? So I'm going to draw the homotopy groups. So what are the homotopy groups of BP brackets 1? Pi star equals Z localized at P. I join V1. So I'm going to draw them like Adams charts. So this little tower over here, here's P, and then here's V1. So all these little upwards arrows, if you don't know about Adams charts, these are supposed to be copies of Z localized at P, and it's like a polynomial algebra on V1. Now, so that's pi star of x. Now here I'm going to put pi star of BP brackets 1, where I rationalize it. So that means I need to take these arrows and invert P, so they go up and down now. So the Z's turned into Q's. Over here I'm going to write pi star of BP brackets 1 K1 localized. Now this is a kind of intimidating formula, but in this particular case it's very easy to compute. It's just inverting V1. This formula is just compensating for the fact that V1 might not be there. So I'm just inverting V1. I'm also, let me just not worry about this. Okay, I'm also P completing, but that's sort of neither here nor there. So that's here. I inverted V1, and then this picture, I need to take this picture and invert P. So pi star of BP brackets 1 of K1Q, I have this picture, but then my vertical lines go both ways. Okay, and the point is that what I have here in red is that you've got like a Meyer-Via-Torres sequence. So now I want to E1 localize this thing. Okay, you've got a Meyer-Via-Torres sequence. So what's in the red here is just the kernel of the direct sum of these two maps going to here. But then you also have to deal with the co-kernel. And so what is in here that's not hit by either of these things? It's this stuff. And so then that comes around with a little shift. In like degree 2p minus 1 minus 1 or something. And this is what you get for the homotopy groups of the E1 localization, a negative cone. Okay? Aha! All right, so now we're ready. Okay, so the strategy now strategy. So there's also a kind of chromatic fracture square in C2 spectra. It's the Tate square of Green-Leeson-May. So here, say Y is a C2 spectrum. I can obtain Y from its geometric localization and its homotopy completion and its Tate spectrum as a homotopy pullback. What are these things? So this homotopy completion is this FEC2 plus going into Y. And this guy here, this geometric localization is Y smash EC2 twiddle plus, where you have a cofiber sequence. EC2 plus goes to S naught, goes to EC2 twiddle.
Beta plus.
Oh, there's no plus. Right. Okay, great. That thing's already pointed. Doesn't need another base point. And then this guy here is the iterated thing. So it's the you take the homotopy completion and then you take the geometric localization. But there's another way to think about these things. Namely, you can also write down this as I can also write down the geometric localization as what I get Y when I invert A. And this homotopy completion, I can also write a formula for it. It's the inverse limit over I of Y smash cofiber of A to the I. In other words, it's the A completion of Y. And so I can also think about the Tate square as an A arithmetic square. Okay, and now the strategy is going to be, oh my goodness, okay. Strategy is to one, understand. So say we start with X, our real motivic spectrum. I want to understand that. So the strategy is one, to understand the geometric localization. Two, understand the homotopy completion. And then, well, I mean, I probably then already know this, but understand the Tate guy. Okay. This first guy has already been solved by Tom Bachman. So the first situation, I start with the real motivic homotopy groups of X. This maps to the C2 equivariant homotopy groups of the realization, but then I can map it out to the geometric localization And remember, this is nothing more but inverting A. So it factors, because the realization of tau, or realization of rho, equals A, this factors through the rho localization. And the theorem, due to Bachmann, is that this is an iso. Okay, so that's simple enough. How about 2? So that's basically what the talk is really about.
What was the definition of the phi in the motivic case?
So that's the geometric localization. That's the y smash EC2 plus.
As an E now, it's this sort of fancy E.
There's no fancy E.
Oh, it's not motivic.
This is equivariant. This gets confusing real quick. Yeah, we're in the equivariant case. Yeah. Okay, so that handles that. So now let's talk about the this other guy. So now I want to understand. So what I'm going to do is I'm going to think about the realization map as a map from. So now I want to understand this, right? So what I'm going to do is I'm going to think about the realization map. So this is. Let me just write it. Stop motivating. Okay. So I'm going to think about the realization map as a map from here to here. Realization. Okay, now the thing to know is that there are also, so the thing to know, so fact, so for j very much larger than I, there exist tau to the j self-maps of cofiber of A to the I. Okay? And the realization of these.
Is that a rho to the I?
Sorry? Oh, rho. Thank you. Sorry. Now I'm getting confused. Rho. And the realization of tau to the j is like a u to the j is an equivalence. Okay? So therefore, this factors through the tau localized guys. So I'm going to call that map, I'm going to call that alpha xi. Okay? And then what I can do, I can think about this. This actually comes from a map of spectra because these are like or a map of spaces. These are natural. So I'm going to think about this as a functor, as a natural transformation between functors from real motivic spectra to spaces. So I could think about this as applying pi 0 to this kind of functor. So here's the space of maps from S star into X smash cofiber of rho to the I, and then I'm going to localize. I'm going to localize those. Oh, not enough room. I don't need to invert anything here because it's already inverted. Okay, there we go. So I can think about these, okay? And then applying pi 0 to these natural transformations gives rise to these natural transformations. Then I can take the homotopy inverse limit of these natural transformations. So applying holim over I get a natural transformation a x infinity from this. Now, when I take the inverse limit over here, I have some funky guy. And then here I take the inverse limit. It's not so funky because it already has a name. It's the A completion of X, otherwise known as the homotopy completion. In other words, what I've got is a map alpha, a natural transformation that goes from pi star x r x smash cofiber of rho to the I, where you localize at tau, to pi star C2 of the homotopy completion. Maybe I should just write it over here. The theorem of me and J is that alpha x infinity is an iso. Now, it's actually surprisingly not hard to prove this theorem if you know a few things. And I was going to just sketch the proof for you, but I'm kind of out of time. So instead, I wanted to show you a picture of this theorem in action. So maybe we can switch to the slides. So it probably goes without saying, but I'm going to say it anyway, that if you apply this theorem to the Eilenberg-MacLane spectrum, you start with the real motivic thing, and then it'll just the same phenomenon that happened in the Ravenel 84 paper will produce the negative cone. Okay? So you might say this explains the negative cone, but we go backwards. We use the existence of the negative cone to prove the theorem, so that's kind of not fair. But anyway, let me show the example of KGL. Okay? So this is a picture of the bigraded motivic homotopy groups of KGL over the real numbers. So you have these circles are Z mod 2s, the boxes are copies of Z. And some of the boxes are actually diamonds. Those are copies of 2Z, if you like, the ideal sitting inside of Z. Here I've got rho, here I've got V1, and this thing is like tau to the 4th periodic. So here's tau to the 4th over here. Okay, and now what I'm going to do is I'm going to do these things. So applying the Bachmann theorem, the geometric localization is just invert rho, the geometric localization of the realization. So you just invert rho, and so that gets rid of all the rho torsion and just leaves you with these copies of this polynomial algebra on tau to the 4th of rho inverse. Now, just in the case of the Ravenel 84 paper, although that formula looks complicated, in effect, all it ends up doing is, wait, what do I? This might be, oh no, this is right. Yeah, this is fine. Yeah. So what it really is doing is just inverting tau. And so this tau periodic pattern now goes on forever. So that's the homotopy groups of the geometric localization. I should say that another real motivating factor in this project was a paper of John Greenleaf's that talks about this, this Tate square viewpoint on these computations. And then there's a Tate thing where I take this and invert rho, and so that's just going to be this. And then what I do when I go back and try and compute the original thing is I have to look at the co-kernel of those two maps, which is that little thing I highlighted in blue over there, and I need to shift it over by one. So there's a couple of blue arrows that I can't reach.
There's a pointer over here.
A pointer. Like totally out
Right
of
there in the corner.
there. Ah.
Yeah.
There is, these lines here are the shifted copy of those lines I highlighted in blue in the previous slide. And then these, and then the rest is basically what you get from taking the kernel of the two maps. And that's the homotopy groups of the realization of KGL. This is a good place to stop, so I will.
We have time for just a couple questions. Doug?
I have a comment. You were worried earlier about whether the cofiber of A is the ordinary suspension of G plus or the twisted suspension of G plus, and they are the same.
That's what I was trying to say.
They're the same.
They're the same, exactly. That's what I'm trying to say. It doesn't matter.
Tyler?
So this says you recovered the C2 equivariant spectrum from the rho inversion and kind of the tau inverted rho completion.
Yes.
Can you kind of go in reverse and say, if I have a C2 spectrum, I can construct a motivic spectrum kind of by taking the homotopy fixed points and finding something where tau doesn't act invertibly to play the role?
I mean, I'd say that would be the program that this Nicola Rica's proposal for MMF, and then I think Mike Hill has something for like KQ or something, doing something like this. But it's very handicrafted. There's not like a general. I don't know of a general way of doing it. It's like, because typically what you do is you manually prescribe what you want on the geometric side, on the geometric corner.
Okay, real quick, Mark. Yeah.
Yeah, I mean, just a comment to the comment, that's kind of like a block-Pareto conjecture, saying that you have everything as a truncation of the dot localization in some sense. But do you have computations for things like KQ, the Hermitian?
So the idea now is to take this into the in the computational direction, and I'm hoping to partner up with some folks. Like I've mentioned this to Dan, I've mentioned this to Bert Guillou. So the future work now is to do this for KQ. Recover the KQ computations. The sphere looks absolutely fascinating. So I want to do the sphere, but.
Let's thank Mark one more time.